Hello everyone, welcome to Dakshana e-classroom program. So today we are going to discuss about transistor as device, and before that, based on the biasing of two junctions of transistor. So this is a just one NPN transistor connected in common emitter configuration. So like there is a potential drop across base emitter and collector junction. Based on these potential difference, the biasing of two junctions, base emitter and collector, basically you can say collector and base junction, can be different. So based on the biasing, the transistor can be operated in mainly four modes, and those modes are, so one is active mode. In this mode you can write actually the base emitter junction, I will write it simply BE. So BE means base emitter, base collector junction. Similarly, so in active mode here, BE is in forward bias, FB means forward bias, and collector base junction will be reversed bias, RB means reverse bias. So if this transistor is operated in this biasing, then it will be in active mode. And similarly, another one is saturation mode. So when it is connected both base emitter in forward bias and base collector or collector base junction is also in forward bias, then your transistor will be in saturation mode of operation. Another one is cut off mode. Actually, the behavior of transistor in all these three modes is different. That's why it's important. Actually, we will see that transistor act or work like an amplifier only in active mode. Transistor can be used as a switch when it is operated in saturation and cutoff mode, is it? So that's why it's like important. So cutoff mode here, in case of base active mode, we have seen here the input output characteristic. So output delta IC versus delta VCE for fixed value of IB. So the variation looks like this. So here this is actually active mode, where your IC current is almost constant. This region is saturation, and you can say when IB is equal to 0, then this will be in cut off mode. So these are actually like different. So the behavior here, current is, you can say, constant almost, and there like when IB value is fixed, in that case IC will be also fixed. So cutoff mode here, both base emitter is also reversed biased and collector base junction also reverse bias. When both are reversed bias, then it will be in cutoff mode. Another is inverse mode. In inverse mode, it's sort of inverse of saturation mode, and that is basically base emitter, it's reverse bias, and collector base junction, it's forward bias. So these are four different modes of operation of a transistor. As I told, for active mode or like for using transistor as an amplifier, we will be operating it in active mode. As a switch, we will be operating in saturation and cutoff mode. Let's see how it is operated, how it is acting, how it is behaving like amplifier. So next we are going to see how an transistor can behave like amplifier or act. Okay, so let's see next how transistor can be used as an amplifier. Before that, I think everyone must be clear what is the meaning of amplifier and what is the meaning of amplification, how like transistor act like amplifier. So amplification means like sort of increasing or multiplication. when a weak signal is given as input, and if the strength of that weak signal is increased to like say high in output signal, we call this is amplification. So amplification is the process of raising the strength of a weak input signal to a strong output signal is called amplification. So in this situation, let's say amplifier is working common emitter transistor here, which is an working like amplifier. So here what happened, we give input to it actually and we get here output. So let's say here we have one signal and its strength, you can see it's like less, and the output signal will have more strength. Here this is the input signal, and here we are getting output signal. You can see the strength of output signal is greater. Definitely transistor or amplifier does not change here frequency of output signal remains same, only amplitude is increased, amplitude is amplified, increased. So this is the process, this is how a transistor is acting like an amplifier. Now next point is to work a transistor or as an amplifier. Let's see how we need to connect the things actually. Again here I am talking about the transistor in common emitter configuration. So let's say this is the connection of transistor. Here we have one NPN transistor, this is emitter and this is base and this is collector. So this will be like emitter, that is N, base it's P, and collector also N. Here we have one micro ammeter to just measure the current, input current, here milliammeter to measure the output current. And the point is to work or to act a common emitter transistor as amplifier, it must be operated in active mode, only then it will work as amplifier, right? Another point, as I told, for active mode what will happen, the base emitter junction must be in forward biasing. Now the point is, another thing is, so here we will provide some input signal, this is your input signal given to base emitter, this is input side, current will be like here this way and emitter current here IE, and this is delta IB, delta IC, and here delta IC. We write this output here, we are giving another, this is VCC. And why we need this one actually, because you know if this is a AC signal, then when it's like fed like voltage, then it will be positive, it will be negative, and depending on even the strength, how much is the magnitude, maybe your transistor is in active mode, is in a base emitter junction is in forward bias only for this reason, then this remaining will be like simply gone, it will not be operating on this part. I hope you are getting. So that our transistor is always in active mode means the base emitter junction is supposed to be maintained in forward biasing always. We need to apply some constant potential drop across base emitter. That can be done by connecting a battery VBB. So this battery is actually helping in maintaining this base emitter junction always in forward biasing and this in always reverse biasing. That is why we need these batteries. Here is the input signal and the current is going here, and in this case the output is taken through this and we connect here one load. The potential difference across this will be taken as output, this we call load resistance or output resistance also. So here we are getting actually output signal, and that will have higher strength. So this is output signal. I hope you understood why we are using these VCC and VBB batteries. So this is the circuit. Here we are feeding, the input signal is fed here and its strength is low, and here we are getting output signal of high strength but same frequency. Point, it must be operated in active mode. To operate in active mode, we need to connect these two batteries. So now what is happening here, actually how this is acting like an amplifier. So small signal is fed here, and we know actually that this in active mode I can get here, this is delta IC divided by delta VCE, and this is your output characteristic of, you can see here actually. So this is, let's say, 10 micro ampere, 20 microampere, 30 microampere, and let me see here the current is some 1 milliampere for 10 microampere current, and this is some 2 milliampere, and that is some 3 milliampere, so on is the output current. So now what is happening here, when this current, there is some change in the input current, means this is your IB or delta IB, is it, and this is your delta IC. So then I can say when there is a small change, this is simply maintaining constant current because it's DC, but this signal will increase or decrease, change this input voltage. So you can see this will be like del VBE, and this potential drop you can write delta, or I will write VCE. Okay, so here what will happen when this is changing from 10 to, let's say, 10 microampere to 20 microampere, you can see the output current is changing from 1 milli to 2 milliampere, is it? So I can write delta V or delta IC divided by delta IB. This will be what, 10 milliampere. Delta IC will be 1 milliampere, and this will be like 10 microampere. So you can say this is almost 100. You can see the output current is almost 100 times. So the output voltage will be RL multiplied by this will be 100 times almost, you can consider, depending on input and output resistance. So that way you can understand that here our output current, this is like increasing. When we are making small changes here, the change in this side is higher. That is why it is working, it will be acting like an amplifier. So let me just show you different calculation. I hope the point that how it can work like an amplifier, that should be clear, because by maintaining this forward biasing, small signal is fed here, so that will change in this voltage, and this voltage will basically appear change in delta IB also, as this is controlled, IC is controlled by delta IB. But the point is, when change in this current is small, the change in output current will be large, and that is almost 100 times. This is just for one case, it may be even 200 times also, depending on the parameters of the transistor. So this way, like output current is magnified, it's amplified, and here we are getting a signal taken as output, and you can see here the output signal is also amplified. So let me show you some calculation part and some amplification factor, or like gain, voltage gain and current gain for this system. So in this situation, first one is when, let's say, no signal input is given, right? See it. Okay, so just calculation part here. So when no signal is here, if I apply KVL in this loop, then I can write my VBB minus VBE equal to 0, right? So, and if there is some change in this, means delta VBB minus, I'm like, actually VBB is kept constant, so this is the relation actually. And next case is if this is some signal is faded, so when input signal is given, in that situation there will be some delta V signal. I will write here VBB plus delta V signal, I am taking it plus, and here it's minus VBE, and plus, because of this there will be some change, so delta VBE equal to 0, this quantity is equal to this, so here this change delta potential drop because of signal voltage will appear as change in delta VBE, right? Another thing, so this is for input side. Similarly, I can write things for output side. So output section or output side, this is your delta VBE. Here what I can write, actually this is VCC minus IC into RL minus VCE will be 0. And if there is some changes on this side, because you can see this quantity is remaining constant, so here I will write, first thing is output is what, this actually. So if I some changes, then changes across this delta VCC minus RL into delta IC minus delta VCE equal to 0. So this quantity will be simply 0, and here we can see this delta VCE is equal to RL multiplied by delta IC minus, and this is also your output voltage, right? This way we are getting, so this quantity is your output voltage, right? Just notice here there is one negative sign actually, so this negative sign is implying that output signal will be out of phase by or phase difference of 180 degree, is it, compared to input signal. So your output signal will be having phase difference of 180 degree, or you will say out of phase by 180 degrees. So I hope this is clear, that how a transistor, simple principle here. The point is this input current controlled output. Input current is small, output current is large. So here if small changes occurring in this, that is with the because of this input signal, that will result in large change in output current, and that we can get large change in. Do you know any amplifier device? I think everyone must be familiar with that. We uses some loudspeakers and we uses some mics. So when you are speaking, the voice of actual person is very less if you see the strength, but when audience it's public, is a crowd is there, we use a speaker, and those speakers actually increase the intensity or loudness of that sound to many times. That is because of it, that can be done with the help of amplifier. So let me just tell you some gains in this transistor as an amplifier. Sometimes these questions are asked, problems are asked, you are supposed to find voltage gain, current gain, power gain. What are those terms actually? So current gain, here we write current gain AI, so this is delta IC divided by delta IB, and you can see this is equal to what? It's equal to beta. So this is called current gain. Similarly, we can write voltage gain. gain, then voltage gain is, I can write A V is delta V output divided by delta V input, and delta V output is what? This you can write, this delta V output, we are getting this minus sign I'm not using, I'm just calculating the magnitude, so this will be delta IC multiplied by RL, and if input resistance is RI, then I can write delta IB multiplied by RI. This delta VBE can be written as, or this is a delta V signal, this is change in input voltage, and that can be written as R input multiplied by delta I input, that is IB. From there I can substitute here, so simply you can get, this is also sometimes called as what is this term? This is simply beta, that is your current gain, multiplied by RL output by input. So voltage gain is also expressed as current gain multiplied by this quantity is also termed as sometimes resistance gain. So this is voltage gain of transistor. Similarly, the power gain, so this is AP output power input power, this is equal to what? Delta V output multiplied by delta IC divided by delta V input multiplied by delta IB, right? Power, voltage into current, voltage VI is power. We know this delta V output by delta V input is what? Beta times this, and this quantity is beta, so the power gain can be beta square times RL divided by RI. So these are different gains. So if anything is asked to you, I will solve some problem, some example based on this, so then you can use these relations and you can calculate the gain. So I hope you understand. First thing is, transistor to use as an amplifier, we must need to operate it in active mode, and how it is amplifying, that should be also clear. Output things are controlled by input. The advantage that we have here is that a small change in input create large change in output current and similarly voltage, and that is the main factor which like enable us to use transistor as an amplifier. So this is about transistor as an amplifier. Okay, so next application or next transistor as a device is using transistor as a switch. So the meaning of switch, I think everyone understand, it means on and off or high and low. So how this transistor can on and off and how it can create high and low, let's see that. The circuit for using transistor as a switch is shown here. Let me show you. Here we have this input voltage, we call it VCC, that is variable, it need to be changed, so that's why it's variable. This is base resistance or resistance connected to base, you can call it input resistance. Microammeter, ampere like ammeter, just to measure base current. IB, potential drop across base emitter, VBE. On this side we have this VCC, which is providing voltage for biasing across this junction, collector, base, load like output resistance or load resistance, and output current IC, milliammeter 1 like ammeter to measure current, and here the potential drop across collector and emitter junction is VCE. So this is the setup. We give actually, like, we are not here using transistor as switch in like we will not be operating it by hand, means like we are like pressing it on and off. Here this transistor is operated by changing this voltage actually. So this is input voltage and here we are getting output voltage. Remember that it's taken output across these two terminals. Okay, so let me right, by KVL on input side. Okay, so KVL on input side, then what we are getting, this is VCC minus IB RB VBE equal to 0, and from here I am getting VCC equal to IB RB plus VBE. This is also called input voltage. Similarly, on output side, for this side I can go KVL in this manner: VCC minus IC RC IC RL minus VCE equal to 0, and here this is output, so you can write VCE equal to VCC minus IC RL. This is taken as output. Clear? Now let's understand how exactly this system or transistor here is acting like a switch. Okay, so the point is, here we change this input voltage, right? Let's see the behavior of input and output voltages. If we are changing input voltage, then how output voltage behave, how output voltages change. So here this I am drawing V output versus V input. Now see here, initially when this voltage is very low, what will happen? Very low means it's like so. Initially when Vi is low, starting from 0, so you can take it almost 0, or you can write Vi is less than 0.6 voltage. 6 voltage is some like this voltage across this junction or potential barrier across this base emitter junction. So when this is even less than this, what will happen? Can you see? Base emitter junction will be in reverse biased. Will it allow any current? So if this is the condition, then you can write the IB will be 0, as base emitter junction will be reverse biased. Remember that. If IB is 0, we know that beta is equal to IC by IB. This implies IC. I told you already, in transistor, output current is controlled by input current. This will be beta times IB. So if IB is 0, then I can write IC is also 0. Clear? When Vi is very low. If IC is 0, what you can say? What is the output we are getting? Output is IC is 0, so we are getting output. V output is VCC as this quantity, and you can see this is the maximum, and this is the maximum output voltage. So when input voltage is very low, and you can see this is maximum, and that will be like here, this is VCC, right? And as you increase this Vi, as I increase Vi, what will happen? After some time it will be in forward bias, so your IB will increase and input voltage also we are increasing. That's why IB will increase, IB will increase, IC will increase, and IC will increase means this quantity will increase, and you can see as this quantity increase, this output quantity will start decreasing. So as IB is increased implies IC also increases, and that implies IV output start decreasing. So if I plot simply the variation this, then it comes here like this. This is cutoff region mode, like transistor is in this state in cutoff mode. It is active mode. This is saturation, right? So in saturation here, like what happened in case of saturation, here you can see the output current actually does not vary, or you can say the output current become almost constant. So this output voltage will be very low, or it's like almost zero. So this is the output voltage that you can write, very low output voltage. Now see here, if we are maintaining the input voltage Vi in a manner such that either it is here or it's directly switching to this side. In this case, what is happening? So when transistor is entering into saturation mode, you can say IC will be maximum and it will be constant. So when on increasing this, we input an IB, transistor is in saturation mode. That means IC is max. Now in saturation mode, IC is not controlled by IB anymore, like because it's in the maximum. So in that situation, you can write V output will be almost, you can write VCC minus IC, and this is max into RL. So you can write this quantity will be minimum or low. We call it low, right? So here what we are getting is that when input is low, we are getting high, output is high. This you can also write high. And when input is high, then we are getting output as low. So we maintain the input voltage in a manner such that either your transistor is in cutoff mode or in saturation mode. In that case, for low input we are getting high output, and for high output we are getting low input. And you can see actually low input is putting this transistor in off mode, right? So that way, because here you can see the IB will be 0 when Vi is less, IB will be 0. So this is putting the transistor in off mode, and when it is like high, it will be in, like you can say, on mode. So that way the transistor can be used as a switch. And here the point to be noted is that, so let me just first erase this point, this part. The voltage or input voltage is regulated in a manner such that it either in means transistor either in cutoff mode or in saturation mode. In this condition, for low input we are getting high output, and this putting the transistor in off state. For high input we are getting low input, and that putting the transistor in on state. So this way we can use the transistor as a switch. Remember that it must not enter into this region, that is active mode. So it must be operated in cut off and saturation mode only for using transistor as a switch. So this is how transistor can be used as switch. I hope this point clear, that how we can use. Remember that low input putting this IB current 0, because the transistor here Vi it's almost 0, so it's in basically what, it's in this base emitter is in reverse bias, IB becoming 0, and that putting this transistor in off state. As we are changing this Vi directly to this region, so that transistor is going to from directly cut off to saturation state. In that condition, this is what, maximum, you can say more, and this is maximum, implies IC is also high, IC also maximum, and that will bring, or that will put this output voltage as low, or that is almost equal to 0. So this, in this condition, the transistor will be in on mode. So that way we are using a transistor as a switch. I hope this part is clear. Let's see the next part when we are using transistor for oscillator. Okay, so let's see that next part. Okay, so next is transistor as a oscillator or as an oscillator here. This is a circuit actually which generate undamped AC signal without any externally applied input signal. So let's suppose for some circuit you want some AC signal of some particular frequency, and that too with like constant amplitude magnitude without like or you can say undamped signal. Then how we can generate? So we have seen in earlier chapter that there is a LC oscillator circuit. So if we are having one capacitor and inductor connected this way, then if some energy is given to either capacitor or inductor, then it keep on oscillating and it can generate one AC signal. So if from here, this is called tank circuit, and C and L, then the frequency here C is used variable capacitor. C is a variable capacitor because if we want to change the frequency of this signal, then we need to change this C. So and the frequency of signal generated here is 2 pi under root LC, 1 by 2 pi under root LC. So if we want to change the frequency of the signal, then we can change C or we can change L also, but normally we keep variable capacitor. This is called tank circuit. Actually in that chapter we discussed that here, because inductor and capacitor, neither one is dissipating some energy, so here we get a constant like or undamped. We discussed that that was the ideal situation. If we look at it from practical point of view, then I know these two are not dissipating, but the wire that we use is also having some resistance, so that result in some dissipation of energy. So if we look simply from this circuit, then the signal that we will get will be a damped signal. Actually its amplitude will keep on dying, and after some time it will be over, it will be finished. So this is the damped signal, right? But we want an undamped signal where the amplitude must remain constant. So then what can be done, is it? And another thing is it needs to be amplified. So this is a actually tank circuit which is an LC oscillator. This is tank circuit, LC oscillator. This is the primary source of generating AC signal, and this signal is actually fed to amplifier. You can write CE common transistor amplifier. What will happen actually? So this signal is fed to this amplifier. It will amplify. Here we will get amplified output, and that will be AC signal. But the point here is that this will keep on dying, right, if nothing is done here, and this will amplify. So overall it will be amplified, but it will be a dying amplified signal, and that is also not our requirement. It just simply here it will amplify this here and it will be amplified here, but if you compare the signal strength here and there, it will be different still. So we are not still getting undamped. So what we do is actually that we need to feed, we need to have some like energy supplier, and that should be exactly placing the energy. Energy must be supplied exactly according to the requirement and exactly in this manner, in exactly the same frequency. So for that what we do is actually we fed a part of this output signal. So the part of this signal is fed back to this, is it? So this system complete generate, and here undamped AC output signal, right? some audio generators and like video also. All these files are actually some AC alternating source of voltage and current. Those generated by these LC oscillators actually, or we can generate those signals with this LC oscillator. We want to control the frequency. For that, variable capacitor is used, and this way. So next point is like how exactly I hope this is clear up to here. Another point which I want to mention here is that in this is the simplified block diagram for for using LC oscillator as transistor as LC oscillator, which is actually generating an undamped AC signal without providing any external input AC signal. Next point is, I told that this amplifier actually generate an output which is out of phase compared to input signal by pi or 180 degrees. So if we are feeding a out of phase signal here, then again there will be problem. So that need to be resolved. So to solve that, actually we use, here we have one coil having, let's say, inductance. This signal is also fed to another coil, and these two, like this output signal fed to this LC oscillator through a coil. That coil further will change the phase by 180 degree, and then we will have a signal fed to hit exactly in same phase. How much? Because we know actually it's only small decrease is there, so the quantity that we need to feed to this circuit must be controlled, and that is controlled by the mutual inductance of the coil, LC oscillator coil L, and one coil through which this is fed. So let me first draw the circuit, then it will be more clear to you how it is fed. Okay, so the proper setup for generating this undamped output signal, AC signal, is this actually. So this is simply a tank circuit. You can consider this is your tank circuit. This part is tank circuit, which is originally generating an AC signal. This signal is fed to this transistor, which is a collector, base, emitter, NPN transistor, which is amplifying the signal and sending it here, and we are getting it actually as output signal. But the problem here coming was that first thing is the output signal is in out of phase. The output signal from amplifier is out of phase, or you can say by phase angle, 180 degree angle to input signal. So the point is that we can't feed this output signal directly to this LC oscillator. We need here positive input feedback circuit. Positive feedback circuit. This is positive feedback, which is, and positive feedback, so this we are getting here output, and the part of this is fed back to this, and that is like by an inducting coil. So here we know actually inductor, it opposes, like, right, by Lenz's law, the way it is varying exactly the output signal here, it will generate in opposite phase actually here. So that will be fed, and this M is the mutual inductance between coil L1 and L2. So here this M, it is the mutual inductance of coil L1 and L2, and by controlling this mutual inductance here, we can control how much signal must be fed back to this original tank circuit. So M, coefficient of coupling, how much we need to couple, is it control the amount of feedback. signal. Right? So in this case, and because it is an inductor, so this whatever the signal is coming here, it will generate an EMF that will oppose that change which is entering this, so that oppose will be like exactly in phase with the original L, and that way we are getting it positive. And this circuit, and here we are getting a output signal which is undamped, and this way in transistor is used here as an oscillator to generate an AC output or AC source of undamped or undamped signal. And here like we can define the current gain or the output gain here for this. So here, if let's say this is originally the potential drop, here is Vi, which is the input voltage, and here we are getting output signal V output, then the voltage gain or gain of the circuit you can write without, if I write without feedback circuit, I will write the gain is A, and that is equal to V output by V input, and gain without gain with feedback, positive feedback circuit. So now what is happening here, m some small m times this actually I will write V output will be farad, because it's a fraction of the output, its complete is not farad. So then in this situation the next input will be, when feedback circuit is used, V input plus m V output. So here feedback like this gain with feedback, I can write V output is still same, this is V input plus m times V output, is it? And here I can take V output out, so this will be like dividing numerator denominator, then it will be A divided by 1 plus m A, and this is the relation of output gain with feedback and without feedback circuit. And we control here m and A so that we are getting a constant or signal of same amplitude and frequency. All that frequency we control by this variable capacitor. And complete this is a circuit that is called transistor as an oscillator, which is generating in output AC signal of desired frequency by changing this here, and undamped signal of constant magnitude, constant amplitude and energy. And this is all about using transistor. First we studied about transistor as amplifier, so you must have understood that there the basic parameter, basic feature of the transistor is that input parameter control the output, and the small change in input signal result in large change in collector current or output current. And that is the basic property of transistor, which is used as an amplifier, or based on that transistor can be used as an amplifier. Next we saw, and remember, transistor is used as an amplifier in active mode, and to use transistor as an switch we need to operate it in cutoff and saturation mode. So we vary the input voltage in a manner such that one, it is lying directly in cutoff region, another case it is lying directly into saturation region without passing through active region. So for low it's generating high output, and for high input it's generating, we are getting low in output. So it's putting this transistor one in off state, another in on state, and that is why, and that is how we are using transistor as and switch. So I hope you are clear with this part, using transistor as different devices. Okay, so I hope by this time you are clear with the concept of diode, Zener diode and transistor, and these are main part in semiconductor and devices. And if you are clear with the concept, let's see some application, whether we are able to apply and whether we are able to solve some problems based on these topics. So here I have one example, one problem, that is from this like JEE mains paper, and let's see how we can apply and how we can get it actually. So this is the circuit diagram figure given, and the problem is that in the given figure it is given that VBB, this supply voltage, is variable and can vary from 0 to 5 volt. So VBB can vary from 0 to 5 volt. VCC, it's given 5 volt, this is 5 volt is given. Beta DC is current gain, and that is given as 200, right? RB, the resistance for this is 100 kilo ohm, and RC is 1 kilo ohm, and VBE, this VBE is also given 1 volt. The minimum base current and input voltage at which the transistor will go to saturation will be respectively. So here you are asked to find minimum base current and input voltage at which the transistor will go into saturation state. So the only thing here you require, the concept is that you must understand the meaning of transistor into saturation state. So as I told, actually saturation state means the current IC is becoming maximum, and at that point the potential here, so transistor, let me write it, in saturation state, this means IC is max, and that implies V output is equal to VCC minus IC into RC, and when it is max, this is 0. That is the point you must know it actually here. Once you are aware of this point, then it's easy, straightforward. So the thing is, we can get the IC, the current at which transistor will go into saturation state. So here this is output is 0, so VCC is given 5 minus IC I need, and RC is given as 1 kilo, so means 10 to the power 3 equal to 0, and this implies I am getting IC is 5 milliampere, and beta is equal to IC by IB, and this implies the minimum base current corresponding to this IC can be given as beta, that is IC 5 into 10 to the power 3 divided by 200, and that will be 25 microampere. So this is the minimum base current at which transistor will be in saturation state. Another, it is asking input voltage at which it will be in saturation state. So for input voltage I can get KVL in this. So VBB is the input voltage. So if I apply KVL in the input circuit, KVL in input side, then what? VBB minus IB RB minus VBE equal to 0, and VBB, and that is your V input, is coming out to be IB RB plus VBE. Let's substitute IB, we are getting it's 25 10 to the power minus 6, RB is 100 kilo, and plus 1, so this is 2 and 3 5, and here so you can just getting it to 2.5 plus 1, and that is 3.5 volt. So this is the B input voltage at which your transistor will be in saturation state. So you can see how easily we are able to apply, we are able to get. Let me solve more problem that has been asked based on transistor in your previous exams. So the next problem, okay, so see here we have one more problem. This is also from previous JEE main paper. So see the problem. In CE, common emitter amplifier circuit built using an NPN transistor, this is our NPN transistor, and as shown it's beta DC. So data given here, beta DC is 250 and RC is 1 kilo ohm and VCC is 10 volt. What is the minimum base current for VCE to reach saturation? So this is also exactly similar problem. I think you can easily solve it. So here saturation we already mean. So saturation means you can write V output or VCE equal to 0, and that implies this will be equal to what? VCC minus IC into RC equal to 0. So this implies IC is equal to VCC divided by RC, that is 10 divided by RC is 1 kilo, so 10 is to power 3, and that is coming out to 10 raised to the power minus 2 ampere. And we know beta is equal to what? IC divided by IB. This is the collector current corresponding to saturation state of transistor, and this is the relation between like collector current and base current, and by using this we can get the corresponding base current, and IB is equal to 10 IC divided by beta, and that is 10 raised to the power minus 2 divided by beta is 250. Solving, we are getting IB is equal to 40 microampere. So this is the minimum current, base current, for which the transistor will be in saturation state. So I think you should be clear with this problem also. Okay, so let's see the next problem, also same based from previous JEE main paper. So let me first read the problem. An NPN transistor is used in common emitter configuration as an amplifier. So NPN transistor, common emitter configuration, using as an amplifier with load resistance. So load resistance means you can write it, output resistance is 1 kilo ohm, and a signal voltage of 10 milliampere is applied across base emitter. So means delta VBE will be delta V signal is 10 milliampere. This is also given. This produces a 3 milliampere change in collector current. So that means delta IC is equal to 3 milliampere, and 15 microampere change in base current. So that means delta IB is also given 15 microampere, right? Next, change in base current of the amplifier. The input resistance and voltage gain is asked to you. So this is the, so first thing is like we know actually here we have delta VBE and IB. So from there I think like you must be remembering the relation that delta VBE is equal to I delta IB multiplied by R input. V is equal to IR, and this implies I can get directly R input is coming out to be delta VBE divided by delta IB, and this is what, 10 milliampere minus 3 divided by IB is just delta VBE. Yes, that's correct. And I'm getting here delta IB is 15 micro, so 10 raised to the power minus 6, and this implies we are getting it's 10. Just check the calculation part. Okay, so that's correct, and see here, so this is the 10 to the power 4, you can write, divided by 15, that will be 0.67 kilo ohm. So this is the input resistance we got, and next it is asking voltage gain, right? So voltage gain, we know actually AV is equal to beta times R output by R input, and beta, so I need beta, and beta we have already relation, that is delta IC divided by delta IB, and this is 3 milliampere divided by 15 microampere minus 6. So this coming out to be beta is 200, and if we substitute there, then voltage gain, AV is voltage gain is beta is 200 multiplied by R output, how much, 1 kilo ohm, R output 1 kilo, so 10 raised to the power 3 divided by R input is 0.67 into 10 raised to the power 3. This simply gets cancelled, and 0.67 is also equal to what, 10 by 15. So this is equal to 200 into, this is 15 divided by 10, and we are getting AV is equal to 300. So this is your voltage gain for NPN transistor used in common emitter configuration as an amplifier. So you can see we are straightforward getting the answers. I hope you are clear with the transistor part. You solve more problems based on it, and let me solve some problem based on diode using as Zener diode, is it, or using Zener diode as voltage regulator. There also some properties are there, you just need to remember them, you just need to understand them. For that, just go through the lecture part. I hope you will be clear with the properties and the theory part of this basically concept. Okay, so here we have another problem. In the figure, we are asked to find the potential difference between A and B, and here we are given a circuit with the diode. So this is your diode, and now it's basic problem on diode. So first thing is positive, negative battery. You can see the potential here will be higher. So this diode is in what? You can say it's in forward bias, and we must know that how a diode behave in forward bias. So the equivalent circuit will be this. Diode in forward bias behave just like a wire, conducting wire. 10 kilo ohm, 10 kilo ohm, this is also 10 kilo ohm, and this is 30 watt. The equivalent circuit, these two are in parallel and in series, so you can get it basically simple. Now it's nothing in the problem. This is 5 kilo ohm, this is 10 kilo ohm, and these are A, B terminal, and this is 30 volts. So the current through is given by 30 divided by resistance, that is 15, and VAB is equal to I multiplied by R, that is this multiplied by 5, and we are getting this is 10 volt, and this is your answer. So this is using basic property of a diode, right? Okay, so next problem here is a figure shows a DC voltage regulator circuit with Zener diode. So here Zener diode is used as DC voltage regulator. Now the thing is, here you must be understanding, you must be aware that how a Zener diode act as or work as a voltage regulator. So now this is the situation, and breakdown voltage is 6 voltage. So means when the voltage across this diode is greater than like as soon as it is like reaching beyond this, it will not allow to increase the voltage. It will simply pass the maximum current so that the voltage can be maintained as 6 volts. So across, this is the load across which always 6 voltage will be regulated, maintained, and the input voltage is varying from 10 to 16 volt. And then what is the maximum Zener current? It's saying maximum Zener current, and remember that maximum Zener current will be when the input voltage is maximum, right? So with that we can directly write input voltage should be maximum, means 16 volt, right? But the point is, this can't allow the voltage across this to go beyond 6 voltage, right? So that I can calculate easily load current, and if voltage across this is 6, then voltage across this load will be, because here it's 16, so it will be, right, you can write V across this will be what? 10 volt. Then I can get total this I source, and I can get the current through this. So I load is given by what? Voltage, that is 6 divided by 4 kilo ohm, and that is 6, I'm like 3 by 2, that is 1.5 into 10 to the power minus 3 ampere. Is it 1.5 milliampere? And the net current coming from here can be, because potential difference across this, I know potential drop across this will never go beyond 6 voltage because it will regulate it. So potential, if we apply KVL, simply the voltage drop across 2 kilo ohm will be 10. So the I source current will be what? It's equal to 10 divided by 2 kilo, and that is equal to 5 milliampere, right? So now at this junction you can say that 5 milliampere current will divide some here and remaining there. So I can write IS will be I Zener plus I load, and this implies I Zener is equal to IS minus I load, that is 5 minus 1.5, and this comes out to be I Zener is 3.5 milliampere. So this is the maximum current or Zener current for this range of voltage. So I think like you are clear with this concept also. It's not big issue, it should not be a problem anymore for you people. Okay, so let's see the next problem here. This is also based on Zener diode. A figure represents a voltage regulator circuit using Zener diode. VB, breakdown voltage actually for Zener diode is 6 volt, and load resistance RL, this is 4 kilo ohm, and this is given as 1 kilo ohm. Voltage VB can vary from 8 to 16 volt, and then the minimum and maximum. So I think this is also straightforward problem. Minimum current through Zener diode will be passing for minimum voltage, and maximum current will be for maximum voltage, and the voltage across this will be only 6 volt. Across this also it will be only 6 volts. So I can easily get I load. This is, let's say, I source again, and I am saying this is I diode, Z current, right? So IL will be fixed because doesn't matter how much voltage is applied here, drop across this voltage drop will not going to vary. So let's see, IL is equal to what? So this is coming out with 6 divided by 4 kilo ohm, that is 1.5 milliampere. This is I load. Now based on when this potential drop VB is minimum, then current through this will be minimum. So for minimum IZ, VB should be what? 8 volt. And if it is 8 volt, across this it is 6. Across this it will be what? Across this it will be simply like 2 volts. So I can get IS is equal to, and we need to check actually, let me first calculate straightforward things. So this is coming out to be what? It's 2 divided by 1 kilo means 10 to the power 3, that is 2 milliampere, right? So definitely this current is greater than this, and that means it is possible. Now so you can get here actually that I source is IZ plus IL. Z is coming out to be I source minus IL, 2 minus 1.5, that is 0.5 milliampere. So this is the minimum current. For maximum you can write VB should be maximum, that is 16 volt. So for this we can get, across this it will be 6, across this it will be 10. So I can get I source is 10 divided by 1, that is 10 to 1 kilo, that is 10 to the power, or I can write 10 milliampere. And IL is not going to vary, it's again 1.5. This is source IZ is equal to 10 minus 1.5, that will be 8.5 milliampere. So these are minimum and maximum value of current. Remember that's correct. Minimum value is 0.5 milliampere and maximum value is 8.5 milliampere. So I hope you people should not have even problem with diode and Zener diode. Try more problem based on it, and this is all about your semiconductor part where you people might be facing problems. Just go through these lectures. I hope these lectures and these problems will help you in understanding, and you will definitely improve your score by at least like one question or 1 to 2 depending on maybe 4 to 8 marks should must increase in your next exam. And wish you all the best. Let's see. Thank you.